Hello and welcome to Earth's SciShow, the podcast where we explore the exciting world around us through a geological lens. I'm your host, MrEarthGuy, and today we're going to talk about a topic that has fascinated me for many years, paleoclimatology. Well, what's paleoclimatology? It's the study of past climates, and it's a field that provides us with invaluable information about the Earth's history and helps us understand how our planet's climate has changed over time. To truly appreciate paleoclimatology, we need to first understand what climate is. Climate is the long-term pattern of temperature, precipitation, humidity, and other atmospheric conditions in a given area. These conditions are influenced by many factors, including solar radiation, Earth rotation, and atmospheric gases. And don't forget, if you enjoy this podcast and the topics that we discuss, be sure to hit that follow and notification icon. It really supports the channel and allows us to continue to make great episodes. Without further ado, let's get back to it. To study climate, scientists analyze various indicators, such as tree rings, ice cores, sediment layers, and fossils. These indicators allow scientists to look back thousands and even millions of years to understand how the climate has changed over time. The first paleoclimate proxy indicator which we're going to talk about are ice cores. Ice cores are cylinders of ice drilled from glaciers and polar ice sheets that provide a detailed record of the Earth's climate history. These cores contain information on temperature, precipitation, atmospheric composition, and other environmental factors dating back hundreds of thousands of years. And one of the most significant applications of ice core research is the reconstruction of past climates. This includes looking at atmospheric carbon dioxide levels. Scientists analyze tiny air bubbles trapped in the ice to measure the concentration of CO2 in the atmosphere at different points in time. Ice cores also offer insights into a wide range of other phenomena, including volcanic eruptions, solar activity, and even cosmic events. For example, layers of volcanic ash in the ice can be used to date specific eruptions, providing a valuable historical record of these events. Similarly, ice cores can reveal changes in solar activity over time by measuring the levels of certain isotopes in the ice. These isotopes are created when cosmic rays interact with the Earth's atmosphere, and their abundance in ice cores can provide clues about variations in solar radiation. Ice cores have even revealed evidence of past pandemics, such as the Black Death. By detecting spikes in the atmospheric lead levels associated with increased mining and smelting during periods of population decline. This may be news to you, but ice has not always existed naturally on Earth's surface. This is due to the variation in temperature over Earth's history. This means there's a finite amount of ice that we can actually measure to understand Earth's past. This is where other forms of paleoclimate proxies come in. One example is sediment cores. They are obtained by drilling into the ocean floor or lake beds to retrieve layers of sediment that have accumulated over hundreds of thousands of years. These contain a wealth of information about past climate conditions and environmental changes. Layers of sediment that slowly accumulate on the bottoms of lakes, seas, and oceans gradually enshrine a long-term history of the climate information. For example, rainfall and the runoff it produces washes soils into rivers, which then flows into lakes and seas. As the moving river water, with its suspended sediments, reach the calmer lake or ocean environments, the sediments fall to the bottom, gradually building up layer upon layer of deposits. Likewise, fine grains from distant dust storms and ash from far-off volcanoes can be blown over water, fall to the surface, and then sink to the bottom to join the deposition process. The same is true for organic materials. Microscopic organisms such as foraminifera, also known as forams, and diatoms are commonly used as climate proxies. Forams and diatoms are shelled organisms found in aquatic and marine environments. They come in two forms. We have planktonic, which means they float in the water column, and we have benthic, which means they're bottom-dwelling. Stable oxygen isotope ratios contained in the shells can be used to infer past water temperatures. These oxygen isotopes are found naturally in both the atmosphere and dissolved in water. Warmer waters tend to evaporate off more of the lighter isotopes, so shells grown in warmer waters will be enriched in the heavier isotope. Measurements of these stable isotopes in the shells of planktonic and benthic forams and diatoms have been taken from hundreds of deep-sea cores around the world to map past surface and bottom water temperatures. Researchers may also use foram and diatom population dynamics to infer past climates. Relative abundance as well as species composition in particular areas may indicate environmental conditions. Typically, warmer weather will cause organisms to proliferate. In addition, since each species has a particular set of ideal growing conditions, species compositions at particular sites at particular times can indicate past environmental conditions. This is why sediment cores are an ideal candidate for paleoclimate proxy indicators. They offer insights to a deep history of the Earth's climate. One of the most exciting things about paleoclimatology is that it can help us understand the Earth's natural climate cycles. For example, the Milankovitch cycles are a series of cyclic changes in the Earth's orbit and tilt that occur over tens of thousands of years. These cycles have significant impact on the Earth's climate, and by studying them, we can better understand natural climate variations. The last paleoclimate indicator are tree rings. By analysing the width and composition of the tree rings, scientists can infer information about past conditions such as temperature, precipitation, and drought. The process of using tree rings for paleoclimatology is known as dendrochronology. Dendrochronologists examine the annual growth rings that are formed in the trunks of trees. These rings are formed due to seasonal variations in the environment, such as changes in temperature or rainfall. The width of each ring represents the amount of growth that occurred during a given year. Dendrochronology is really useful as it can be used at different resolutions of scale. You can use it in living trees, which have been growing over the thousands or hundreds of years, or you can use fossilized trees to understand what paleo environments were like hundreds of millions of years ago. But climatology isn't just about studying natural variations in climate, it's also about understanding how humans are impacting the Earth's climate today. By studying past climate changes, we can better understand the impact of human activities such as deforestation, industrialization, and the burning of fossil fuels. The evidence is clear. Humans are causing the Earth's climate to change at an unprecedented rate. The concentration of greenhouse gases in the atmosphere is increasing rapidly, and the Earth's temperature is rising as a result. If we don't take action to address this issue, the consequences could be catastrophic. And the climate record will agree. Of all the mass extinctions that have occurred throughout Earth's history, it isn't the impact event or volcanic eruption which causes the mass extinction, it's actually the changing climate over a very short period of time. And by using paleoclimatology to understand these mass extinctions, we can make better predictions about our impacts and how we may look in the next 100 to 200 years. But the good news is that we can take action. By reducing our greenhouse gas emissions, investing in renewable energy, and adopting sustainable practices. And regardless of the outcome, the evidence is clear. Nature always survives. And that's the end of this episode. I hope you enjoyed learning about paleoclimatology and how we use different proxy indicators to look at the past. If you enjoyed what was discussed, please remember to hit that follow button and the notification icon. I'm your host, Mr. EarthGuy, and remember, stay curious,